according to this law, the statement of the law is said that the force exerted between two objects, these two objects can be particle, can be two planet, it can be one planet, one object. Okay, let's say object 1 is here, object 2 is here. If object 1 has a mass of m1, object 2 has a mass of m2, and they are separated by the distance of r. So according to the universal gravitational law, or gravitational force exerted on object 1 due to object 2, and there is also a gravitational force exerted on object 2 due to object 1. So these two forces is acting in the opposite direction. Okay, let's say this F I call it as F on 1 due to 2, and the other one also F on 2 due to 1. This force we call it as gravitational force. So according to the law, the magnitude of the force is directly proportional to the product of mass 1 and mass 2, inversely proportional to the square distance between these two objects. So if I convert it the proportional sign to equal, you will get it as G m1 m2 divided by r squared, where G is a constant, call it as universal gravitational constant, which has the value of 6.67 times 10 power of negative 11 Newton meter square per kilogram square. So according to Newton's law of universal gravitation, the magnitude of the force is directly proportional to the product of m1 and m2, inversely proportional to the square distance between these two objects. Okay, now I'll let you to consider this scenario. This is an object of Earth, where Earth has a mass of me. For example, I use the capital letter of M to represent the mass of Earth, and here's the center. If I have another object here, which is a smaller object, right, and which is located at the distance h from the surface of Earth. So if Earth has a radius of re, I use the capital letter of R to represent the radius of Earth. Therefore, the distance from the center of the Earth to the center of the object is called it as r. So where r is equal to h plus re. If you refer back to this law, Newton's law of gravitation, the magnitude of force is inversely proportional to the square distance. So this distance is measured from the center of object 1 to center of object 2. So same as this. So I assume that Earth is object 1, so from the center of this object to the center of another object, that is the r, small letter of r. Okay, now, according to this Newton's gravitational law, so the gravitational force exerted on object 1 and Earth as object 2, for example. It can be either one. It can be Earth as object 1, this small object as object 2 also can. So the gravitational force exerted on object 1 due to object 2 or due to Earth is Fg. According to the law is proportional to product of these two masses if the mass of object 1 is m. So m multiplied with the mass of the Earth divided by the distance from the center to the center of the object, which is r. So r squared. And the proportional constant is g. The gravitational force exerted on object 1 is actually same as mg. Therefore, this Fg is also equal to mg. And I will get g m me divided by r squared. So the m and n can be cancelled off. And eventually, you will get the g is equal to g me divided by r squared. Where this small letter of r is equal to h plus re. H is the height from the surface of the Earth to the center of the object. Re is the radius of the Earth. So this g is basically the acceleration due to Earth gravity. While we are learning the projectile motion or freeform motion, we use g, we use it as 9.80 or 9.81 meter per second squared. So actually this 9.8 is calculated based on this expression on the surface of the Earth. On the surface of Earth or near the surface of Earth, g is equal to g me divided by re squared. G is called as gravitational universal constant, which is equal to 6.67 times 10 power negative 11. Me is the mass of Earth. Mass of Earth is actually a constant. So G is 6.67 times 10 power negative 11 Newton meter square per kilogram square. Re is the radius of Earth. It is a constant, which has a value of 6.38 times 10 power 6 meter. Me is another constant, where the mass of Earth has a value of 5.98 times 10 power 24 kilogram. If I use all this value, substitute inside this expression, so you will actually get the G is approximately equal to 9.80 meter per second square. So that's why we always use this. G is equal to 9.80 meter per second square. On Earth or on the near the surface of Earth, G is equal to this value. So that's why the projectile motion that we are referring to, we always assume that the object is very near to the Earth. It's not very far away from the Earth. And if you like to find out that what is the G for other planet, in general, G for other planet will be equal to G multiplied with the M of the planet divided by r square of the planet. So based on here, you can see that as r is increasing, g will be reducing. Acceleration vary with altitude. Vary means change. The value of acceleration change with altitude. Altitude increase, the g value will be smaller. It's inversely proportional to the square of the distance. If you want to investigate problems near the surface of planet, this r is referred to the radius of the planet. Gravitational potential energy. Potential energy, so it's the energy. Okay, we use a capital letter of U to represent it. Definition of the gravitational potential energy is the work done to bring an object from infinity to a distance of r. Work means the F dot with displacement. So this force here means the gravitational force, right? This is the work done by the gravitational force. So to be more accurate, I put a subscript of G below it. So then, according to the Newton's law of universal gravitation, this gravitational force is G m divided by r squared, dot with dr. So from infinity to point with a distance of r. G is a constant, m is the mass of the planet, and this small letter of m is the mass of object. So which means, if let's say I have a planet here, and I have an object from very far infinity, the mass of planet is m, this mass of object is m, so you have to integrate 1 over r squared with respect with r. So for example, you integrate 1 over x squared with respect to dx, you will get negative 1 over x plus c. Negative g m over r plus c from infinity to r. Then we make one assumption. We assume that the potential energy at infinity is equal to 0. If you make this assumption, the c here, you will get it as 0. Therefore, gravitational potential energy U is equal to negative g m over r. So this is the expression for gravitational potential energy. The potential energy is varies inversely to the r in the negative direction. So if you plot the graph, this is U, this is r, inversely proportional. If U is inversely proportional to r. But now U is inversely proportional to negative 1 over r. So you will get something like this. So if you plot a graph, you will get a graph something like this. R is infinity. U is approximately equal to 0. Here is actually same as the radius of the planet. If you are referring to Earth, then this one will be the radius of Earth. When the r is equal to radius of Earth, this value is equal to negative g m divided by r e. You will get the U maximum value when r is equal to infinity. That means U maximum is basically equal to 0. So anything below 0 will be negative. Okay, and U minimum value is equal to negative g m over r e. Potential energy as mgh, right? Is this mgh equal to U? Negative g m over r. So are they the same? Let's look at it. Let's say this is the Earth, which has a radius of re. The mass is me. I have another object, the mass of m, and it is located h from the surface of the Earth. So the total r here, if from the center to center, should be small letter of r, where this small letter of r is equal to re plus h. Refer to this point. The potential energy at this point is Pe2. Potential energy at this point on the surface of the Earth is Pe1, for example. Potential energy difference between these 2 points. So I know that Pe2 is higher than Pe1. So I'm using Pe2 minus Pe1. The potential energy is equal to negative g m over r. I apply this. Negative g m over r. So at point 2, so I will have negative g m, capital letter M is m of the E, m over r. R is from the center of the object to the center of the planet, okay, where the r is equal to re plus h. So potential energy at point 1 is equal to negative g m over r, but point 1 is on the surface of the Earth. R is equal to re only. So this one is equal to re. Negative g m 1 over re plus h. So negative already take out, so here will be minus 1 over re. Negative g m right? I make the denominator common, right? Make the same denominator. So I multiply the first term with the denominator by re. So I will get re multiply with re plus h. Then the second term I multiply with re plus h. In the numerator here I will have re minus re plus h. Re minus re is 0. So this one can be cancelled off. And this is a negative, so negative and negative. So I will get a positive value. G m So this one is already 0. Negative here, negative, negative is positive. Multiply with h divided by RE plus H. I assume that RE is much larger than H. So H is very small. I assume that H is very small, approximately equal to 0. So I can ignore this H. I will get GMEMH divided by RE squared. Gravity on the surface of the Earth, or very near to the surface of Earth, gravity of the Earth is given as GME over RE squared. So basically this one is G, right? Because G is equal to GME over RE squared. And you substitute inside the expression, you will get mgh here. Escape velocity is actually the speed needed for an object to soar off into the space and not return anymore. That's called as escape velocity. And escape velocity is independent of mass of the object. So no matter how big is the object, the escape velocity remains the same. So for example, escape velocity for Earth is about 11.2 kilometer per second. So basically, escape velocity depends on the mass of the planet and also depends on the radius of the planet. So let's derive it out, yeah? Escape velocity. Okay, let's say I refer to escape speed from Earth. If an object is projected upward from Earth with large speed, the speed is large enough, the object will fly to infinity. The object move to infinity. Infinity means far away from Earth and go off and never return. Okay, and this speed, this speed means this large speed is called it as escape speed. The escape speed from Earth is about 11.2 kilometer per second, which is considered very high. Right, and it is important why the Earth must have a very high escape velocity, right, or escape speed. For example, our commercial flight, the plane. Usually the speed of a commercial flight about 250 meters per second. Just imagine that if the escape speed for the Earth is very low, it's about maybe 200 meters per second. So your commercial flight is 250. Okay, already exceed the escape speed. So which means your flight will not return to the Earth anymore. The escape speed for the Earth is so high, our commercial flight is able to fly to a high altitude, but the speed is not yet reached the escape velocity. The average velocity of molecule or gas at a layer of atmosphere around the Earth. So the average velocity of the gas molecule is about 500 meters per second. So if you compare these two, compare with the escape velocity of the Earth of 11.2 kilometers per second. So this 500 is considered small as well. So that's why in our atmosphere, near the surface of Earth, a lot of gas there. Okay, so how can we actually find out or derive out the escape velocity? Escape velocity is independent on the mass of the object. So we may use the concept of conservation of energy. Okay, let's say this is the Earth, and I refer to a point, but this point is called as infinity, very far. And initially, okay, maybe I throw the object upwards with the speed of u. Okay, and I call this point as initial point, and at infinity as final point. So now I'm applying the conservation of energy. E initial is equal to E final. Mechanical energy consists of kinetic energy and the potential energy. So initial, final, I also have kinetic energy, final, and potential energy, final. So kinetic energy initial is half mu squared. Because initially I throw the object upwards, vertically upwards with the speed of u. So the potential energy from the center of the Earth is negative GME m over RE. Okay, where m is the mass of the object. Okay, and at the final point which is at infinity. So when you reach the final point, means this is a so-called as maximum height. So the kinetic energy is equal to 0. So we also assume that potential energy at infinity is equal to 0. Therefore, potential energy at final is also equal to 0 because this final point is actually at infinity. And therefore, half mu squared is equal to G MEM divided by RE. Okay, m and n can be cancelled off. So eventually you will get the u is equal to the square root of 2GME over RE. This u is able to reach infinity and never return back. So this u, we call it as escape velocity. So escape speed of u. So if you are referring to other planet, then the ME may just substitute or replace with the mass of other planet and same as the radius of other planet. Satellite in a circular orbit. there is only one speed that the satellite can have if you would like the satellite to remain in the orbit with a fixed radius. Okay, for example, this is the Earth. This is astro satellite. It's orbiting about the Earth at the fixed radius of r. So in order to have astro satellites always orbits with the fixed radius, so this satellite must orbit with certain speeds. You have to calculate out what is the speed of the satellite must have so that it will always fix at this radius. And basically, we are applying the concept of gravitational universal law and also the circular motion. When an object is circulating about Earth, there will be a centripetal force which is always directed towards to the center of the circle. So this centripetal force, the magnitude is mv squared over r. So the magnitude of the centripetal force is also same as the gravitational force of g me m over r squared, where me is the mass of the Earth and small letter of m is the mass of the satellite. So Fc is basically same as Fg. What is Fc? Fc is mv squared over r. Fg is g me m over r squared. So from here, basically, you can find out what is the speed required by the satellite in order for the satellite to stay at this fixed radius. Speed is g me over r squared root. That is the speed of the satellite that must have. This speed here is independent of the mass of object. So if you compare in one revolution, so we know that the speed is defined as total distance traveled divided by time. So in one revolution, the total distance traveled is 2 pi r, radius means is r, and the time taken is time period. So this is speed. It's equal to the square root of g me over r. So if I rearrange the equation, t here is equal to 2 pi r power of 3 over 2 divided by square root of g me. You can get a relation between the time period and also the radius. Okay, because 2 pi is a constant, g is a constant, me is also a constant. So from here you can find that t square is directly proportional to r cubed. So t square is proportional to r cubed. This is a law, call it as Kepler's third law. Energy is always consists of kinetic energy and the potential energy. So if you refer to satellite, means I have only the rotational kinetic energy because satellite is orbiting around the Earth, for example. And the potential energy here, of course, I refer to the gravitational potential energy. So this is the total energy. Okay, now I'd like to express the total energy of satellite in terms of G, me, and m. Of course, with r also. So me is the mass of Earth. This small letter of m is the mass of satellite. R is the radius of the orbit. Okay. So the rotational kinetic energy of the satellite is half I omega squared. Potential energy is negative g me m over r. I here is called it as moment of inertia. So moment of inertia of satellite in general should be mr squared. And omega, if we relate back to the linear speed, v is equal to r omega. Omega is equal to v divided by r. So omega squared will be v squared divided by r squared minus g me m divided by r. So r squared and r squared can be cancelled off. Oh, so happen you will get back the same thing of half mv squared minus g me m over r. So which means this is actually the translational kinetic energy of satellite if the satellite is moving with the linear speed of v. So tangential speed actually is, this is the Earth. Satellite is here, so orbiting about the Earth. And it is moving with the linear speed of v at this point. And the radius here is r. M, of course, is the mass of the satellite, and me is the mass of Earth. And now, so I'd like to express the total energy of satellite in terms of g me m over r. But now I have this half mv square here, so I like to do some transformation. So how I transform it? So I refer back to centripetal force and gravitational force. So if a satellite is moving in a circular motion, centripetal force is basically same as the gravitational force. Centripetal force of satellite is mv square over r. So gravitational force is g me m over r square. R and R can be cancelled off. Alright, so from here, mv square is actually same as g me m over r. So I want to get half. So I multiply with half here, multiply with half here. So half mv square is same as half g me m over r. So I substitute in to here. So eventually I will get half g me m over r minus g me m over r. So you will get negative half g me m over r. So this is the total energy of satellite.